Okay, so we're going to be focusing on the fundamental theorem of calculus. However, this section's focus is going to be more on part one, which has a lot more uh, variations into how problems can be asked to see if you know it than part two. Remember, part two was just saying, uh, part two, which we've already talked about, is saying you can use antiderivatives to evaluate definite integrals. Um, so the idea that if I find the antiderivative of the integrand, plug in the upper bound, plug in the lower bound, subtract, there's my definite integrals value. Part one, on the other hand, is what leads us to part two. And part one is saying that it's said a few different ways. The derivative of the antiderivative is the function, which we're kind of used to because that's how we check if our antiderivative is correct. But it also means that derivatives and integrals are inverses of each other. They undo each other. So if I have an integral, taking the derivative cancels the integral. If I have a derivative, taking the integral cancels the derivative. So we can see it written as if I take the derivative of the antiderivative, I get the original function. Or if I take the derivative of an integral, I get just the integrand. So we can write these in different ways. So one way of rewriting part one is that is saying that a function is going to be the integral from a to x of f prime plus f of a. And this is what's called an integral defined function. That's where we're going to be spending most of this section. Part two, instead of taking the integral from a to b of f, find the antiderivative of f, I can say find the integral from a to b of f prime. Well, the antiderivative of f prime would be just f. Because I could check it. What's the derivative of f? Oh, it's f prime. That works. Plug in b, plug in a, subtract. Or I could take this and move f of a to the other side. And this is what's called informally FTC with a twist. There's not an official name. It's just one that I've heard bounced around by several teachers. So where we're going to start is with just writing an integral defined function. And the idea of this is being able to find antiderivatives when I don't know the antiderivative. So I'm told dy dx is equal to the tangent of x, and y is 5 when x is 3. And I want to find an equation for y. So with this, what I know is that, well, I need to undo the derivative. Well, to undo a derivative, I need the integral. So I need to take the integral of the tangent. Now, instead of saying the tangent of x, I need what's called a dummy variable. You'll see that I tend to use t, but there's no reason. I just need a variable I have not used already. So I can't use x, I can't use y. Oh, let's use j. And so in this case, j is a dummy variable. It is just placeholding for x because the x is going to have to go somewhere else. Okay. When I do this, that's me taking advantage of this part of the FTC saying that, well, to undo a derivative, I take the integral because that's the inverse operation of a derivative is an integral. But then I have to worry about the plus c because I'm technically finding an antiderivative. The plus c part is right here. This is my plus c. So my plus 5. But then remember I said x has to go in a very specific spot because that's why I need the dummy variable. The x is going to be my upper bound. My lower bound is going to be the x that I'm told we have to go through. And all of this is what y has to equal. And I can even check this. If I take the derivative of this, the derivative of the integral of tangent is derivative cancels integral, leaving tangent. That works. Derivative of 5 is 0, so that's gone. If I plug 3 in for x, I have the integral from 3 to 3, which by the 0 property is 0, plus 5 is 5, y is 5. This is my function. So if I have another one here, and I say, here's my derivative, 9 over 7x e to the x sine x, and it has to go through, and y has to be 4 when x is 17, well then I need to undo the derivative, but I need a dummy variable instead of x, because the x is going to be my upper bound. Lower bound will be the x that I have to go through, and the y I have to go through is my plus c, and there is my function.